But that would be a good way to answer the question. Is there any intramolecular hydrogen bonding here in this one? So, but at least you know a good study now that you can do to test for your own molecules in the future, right? So, yep.
Also, they have later on they have exchanged the sulfur with selenium at the last compound.
On the last compound?
Yeah, the most active compound.
Yep. Yep. Cool. Thank you.
No, it's from a Germany group. China.
Yeah, see, good. At least we have one person who took this seriously, and no one from our group, right?
Well, he came up afterwards to talk about it also, and so I gave him a very direct, why don't you go find it out, because he had a question.
Majority of you are not even know what we are discussing. You know, right? So then see, like we have all access to all the journals here. NIPER is giving all of that. Huge amount of money is paid by the institute to get the free access to all these journals. You cannot access these journals at sitting at home. And then at least we have one motivated person. I'm so happy about it. So good clap for him. So, okay.
Okay.
Then
Yeah, so any other follow-up questions from yesterday?
Like the one homework question you gave in which the fluorine was opposite this one.
Oh, yeah, the position.
So what about it? You want to see?
Yes.
Let's see, is this the one? This is the other one that we did not do in class, right? Yep. So we have, gauche conformations here, gauche interactions there, gauche interaction there. So the two positions stabilize opposite conformations, or the up versus down of that fluorine atom. So you have, cool? Makes sense? Does it match what you were thinking or what you wrote out last night? Should I make people turn in the homework from last night? We can grade it. Just kidding.
yeah, this is just I wanted to. This is very interesting example because it is there is a 1, 2, 3, 4, 5 member ring, right? And now you could see that because actually I did little bit stereochemistry. So if you see 5 member ring, then when they flip like in cyclohexane, you can see the flipping. But here, say once you flip it, okay, so you can see that the OH which is on the top is going over there, okay, hydroxymethyl group, and then the O in the ring comes up. So this is very interesting thing to see.
Okay, should we move on to new material? So I'll switch out of that slide deck and get into the new slide deck today. We're talking a lot about pKa, acidities, basicities. We'll talk about how basicity and acidity relates to distribution of drugs throughout the body. And then we'll also move into some select examples. So the second half is going to be a lot of detailed examples, particularly in the realm of neurological disease. So how will molecules enter the brain or get rejected from the brain? So that'll be a specific subtopic for the second half. But first we need to lay down the basic principles. We need to talk about some of the basics about how compounds move throughout the body. If I can't reinforce it enough, we want to think very critically about the physical organic chemistry and understand how the physical organic chemistry relates to perturbing the properties of molecules, and then we apply that in the context of biological settings. Okay, so all these principles here that I talk about so much and spend a lot of time talking about are the foundation for understanding the distribution, metabolism, and pharmacokinetic properties that are still essential for drug discovery. Okay, so be a physical organic chemist first, and then apply that to the understanding of the science of the interface of chemistry and biology. So today, as mentioned, we're going to talk a lot about distribution of molecules throughout the body, and when we talk about molecules distributing throughout the body, these molecules typically need to get across membranes, whether they're going in and out of cells or across different membranes within the body that are made up of cellular monolayers, or whether they're circulating throughout the body, you need molecules many times to get through membranes. Sometimes you don't. So I'll pause for a second and say, be critical about your own drug discovery campaign. If you're dealing with topical antibiotics, you don't necessarily need that getting into systemic circulation and getting through into certain tissues, right? So you can be thoughtful and critical about the needs of your molecule, but right now we're going to be talking predominantly about systemically distributed drugs where we have targets that need to be accessed from inside the body. So this is what I call the zeroth law of drug discovery, drug design. It doesn't get mentioned much, but it's implicit for the process. So in order for a drug to exert pharmacological action, it actually has to get to the site, wherever the target is. Okay? It makes a lot of sense when you think about it now, and maybe we assume it too easily, but you can be more critical in thinking about it for your own drug discovery campaigns. It'll benefit you. So when we talk about distribution of drugs throughout the body, who knows pharmacokinetic modeling, compartment modeling for PK? Is this a new topic for most people? Yep. Okay. So when we think about, thank you very much. When we think about how molecules distribute throughout the body, we many times use compartment modeling. And what this is a way to model kinetically, pharmacokinetics, they're kinetics, right? To model kinetically where a compound is throughout the body. What's the concentration in different compartments of the body? When we talk about compartments of the body, we might have, you could define models with different compartments. You could have the brain or different regions of the brain. You can have systemic circulation going through the blood. It can get into fatty tissue. That can be a compartment. When you have an oral dose of a drug, the drug that's in the GI tract before it gets absorbed can be a compartment. The compartments can get more and more complex if you need more sophisticated modeling, but there are also very simple models too that can be developed. And again, something I think you'll see more in coursework as you move forward. Okay, so this would be a representative example of a compartment model in which we're looking at different strategies for dosing that drug. We might have an oral drug or an inhalable therapeutic, a spray that goes into the lung, and it's going to either go into the GI tract. Where's my laser? So it can either go into the GI tract there. If it's a pulmonary dose, that's going to be in the lung, right? So that compartment for absorption might differ depending on how we administer the drug. Now, in order for that drug to reach a systemic target, it needs to go from the GI tract or from the lungs into systemic circulation. That's the blood. And after it starts circulating systemically through the body, some of it might be bound to plasma. That can be modeled as a compartment. Some of it can go into fatty tissue or other tissues. That can be a compartment in these models. Who knows where the site of action is, where your target is distributed, but it might need to get into that specific compartment of the body to exert its action. Now, with this type of, and then we have compartments many times that represent the liver for metabolism and or kidneys for urinary excretion based on how you eliminate the drug. And these are, when we do these models, many times we're thinking about equilibria, so the compound can go into that compartment, it can go out of the compartment back into systemic circulation, and that happens as drugs distribute throughout the body. Okay. Now, in order for this compartment model to work properly, we typically assume the free drug hypothesis, and that's over here. So at the steady state of a drug, drugs can transverse membranes. That's not always true for all compounds, but it's an assumption we use for these types of models. Drugs can go back and forth freely across membranes. Okay? Now, additionally, we assume that there's a 1-to-1 ratio of drug across those membranes. Okay? Very simple model. And then the concentration of the free drug in the compartment where your target is exerts pharmacological action. Okay, all that makes sense. It's really basic when you think about it, but we need to be aware of the hypotheses and the assumptions that we have in our hypotheses when we're using these models. Okay, So really, the key point for this lecture is that we need free passage back and forth across these compartments in order to reach the site of action. And many times that's going to require a drug to go across lipid membranes, plasma membranes, using those phospholipids. This is a simple representative monolayer that I have drawn here. In reality, there are glycoproteins and other proteins embedded in these membranes. There are other challenges that molecules will face as they're trying to transverse. Nonetheless, if we have a drug and it needs to get across that membrane, that's really important for exerting biological action in many drugs. Okay? So that's what we're going to talk about today. We're going to talk about compounds getting across membranes. We're going to obviously talk about fluorination and how fluorination affects that process. It's heavily influenced by perturbations to the acidity and or basicity of the nitrogen and oxygen containing functional groups in the molecule. So there's an important perturbation we'll look at here. And again, log P is an important parameter when we're thinking about distribution. And log P is something that I think most people have been introduced to early in coursework. Just a brief reminder of what this is. Log P is a distribution coefficient. It's the ratio of drug that will predominantly exist in octanol versus water. So it's a shake flask method that's used classically. You take your compound, you put it in this octanol water layer, you shake it up in like a separatory funnel, you measure the concentrations on both sides. And if a molecule is greasy, it'll tend to reside in the octanol layer. If it's more water soluble, it goes into the aqueous layer, and that ratio is important for drug discovery. Okay, because when we think about this process of a drug being solvated, when it's on either side of the membrane, it's surrounded by water, it's solvated. The nitrogen and oxygen containing groups are typically hydrogen bonding, either as donors or acceptors with water. But in order to cross the membrane, you need to dehydrate. They're not going to pull water across. Okay, you need to be in a neutral form to get across. And in the membrane, in that layer, that's all grease. So you need to have sufficient solubility in a greasy environment to get through the membrane, but then you need to be sufficiently water soluble when you get to the other side. So one of the reasons why you need a balance in this lipophilicity parameter. It needs to be soluble enough in water so it can circulate throughout the body, but also needs to be greasy enough to make it into the membrane. Okay, so it's a balance of those properties that we're looking for, and the ratios are used in these equations, log P and log D. The difference is in the pH at which these are measured. So when you do these and just put the compound into water itself, that's what we call log P. That doesn't necessarily represent physiological pH. So we use a log D at pH 7.4, and that's where we use a buffer at pH 7.4 so you can account for ionization states that are going to occur in a physiological system. So if you're going to be cationic or anionic because you have acid or basic moieties in your molecule, log D represents the solubility and the two layers better, okay? So we have log P, log D. In the literature, sometimes you see one, sometimes you see the other, and the difference is the pH at which they're measured. Cool? Basics. I know a lot of people have seen this before, but I just want to make sure we're all up to the same page. So optimal log P values based on maybe where your target is throughout the body, what your route of administration is going to be. If you're going to inject a drug straight into systemic circulation, like an IV injection, that can be a compound that's super water soluble. It doesn't need to be lipophilic to make it across like the GI tract. It can go straight into the bloodstream just fine. In contrast, if we want an oral drug or a drug that gets into the CNS, we might need something that's a little bit greasier there. If we want something that we're going to use like on a patch or a cream or an oil that we put on the skin and want that to distribute through the skin and through fatty tissue on the outer, near the surface of your body, we need those to be really, really, really greasy molecules, and log P can be higher in those situations. So you need to know your therapeutic class, where your target is, and then you can establish a drug product profile, what you're shooting for. And then we can start addressing, is our compound likely going to be greasy enough or too greasy? But there is a little bit of thought in developing your target profile before you move into trying to identify an appropriate log P range. Okay? Okay. If you get too water soluble, you might not get across membranes. But if you have too much lipid solubility, if you're too greasy, and that's a high log P number, you typically face several problems. Number one, you get buildup of drug in fatty tissues. That's a challenge, that's a problem. You might not get to the site of action if the drug is just sitting in fatty tissue. You might have excessive metabolism. We'll talk a lot about metabolism, but drug metabolism predominantly involves oxidation, or one phase of drug metabolism predominantly involves oxidation of grease that facilitates clearance of the drug. And then you can also have drugs that are too greasy, and instead of going through the membrane, they actually just go into the membrane and they sit there. And they don't come out the other side. And that can be a problem if you get a drug that's too greasy. So there are several issues with having compounds that are too greasy. Many individuals will say log P greater than 3 is like undesirable for those three reasons. There are drugs outside of any rules. So even Lipinski's rules. Do we know Lipinski's rules? Everyone knows Lipinski's? Okay, most people know Lipinski's. So there are outliers to Lipinski's rules. There are plenty of them. Okay, so for any of these trends, you can have outliers. Okay. So let's start talking about details of how fluorination can influence lipophilicity. This is actually like the topic that drove my interest when I was a grad student and brought me into organofluorine chemistry. Like it's on this slide right here. Okay. So everybody talks about how fluorine increases lipophilicity. And if you stop and think for a minute about what you're doing, if you put fluorine on a molecule, your carbon-fluorine bond is highly electronegative, has a strong dipole, and if you add a strong dipole to a molecule, wouldn't you think that would increase water solubility? Doesn't that make sense? But everybody says it goes the other way. Okay. And so that's the question when I was, in 2005 or 2006, when I was writing a proposal for my graduate school. We had a requirement that you had to write proposals in graduate school. And that was like the fundamental question, like, what the heck is going on here? That can't be right. That's not true. Why is it, if it is true? Okay? So I'll start to explain that there are different situations depending on where fluorine is introduced on your molecule. It can either increase or decrease lipophilicity based on what's in the vicinity. And then we can understand the perturbations and the why, and then you can use that in your own discovery campaigns. So let's get into the actual data on this slide. So we have it aligned such that we have non-fluorinated compounds on the left, and we have fluorinated compounds over on the right. So that's the big picture organization. You can see the log P values that we're going to compare horizontally between matched pairs. So if we look at that top pairing, you have alkyl systems on the left. You can see the log P values, 1.8 and 3.1. If you add fluorine atoms, individual fluorine atoms to those species, exactly what I mentioned before like what should happen, happens. You introduce a CF bond, you introduce a dipole into the molecule, you increase water solubility, you decrease lipophilicity. And you can see that in the numbers. Look at the magnitude of the difference, about 1 P unit. This is a logarithmic unit, right? So a change of 1.0 is a 10-fold change in the ratio. Okay, so these are all log units. And then, just 0.8 log unit difference there for the slightly longer derivative, okay? So if you have an aliphatic system, no heteroatoms, you put a fluorine atom in there, you increase water solubility. Not what people always say. So let's dispel that myth. It depends on what's in the vicinity of the fluorine as to whether you get an adjustment upwards or downwards. So in the next series, we're going to look at a series of alcohols. You can see ethanol, propanol, and butanol over on the left. And in this series, we're adding a CF3 group at the terminal position of all of them. And here is where you start seeing the increase in lipophilicity. Okay, the magnitude of that, you can see a change of 0.6 log units roughly when you go from ethanol to trifluoroethanol. It's more lipophilic. The magnitude of that change is minimal if that CF3 group gets further and further and further away from the alcohol. So there's something about the distance between the heteroatom, the oxygen, and the CF3 group that's really important for understanding this property. Okay, look horizontally here. We have a 2-carbon spacer, 2-carbon spacer, and you see nearly the same number, and same thing down here when you have a 3-carbon spacer. Basically the same lipophilicity. Okay? So there's something about the distance between the atoms there. And then if the linker becomes too long, we go back to the original effect that we're introducing fluorine and improving water solubility relative to lipid solubility. You see that here. Now we have a 4-carbon linker between this matched pair, and you see the lipophilicity goes downwards. And same thing over here. Now we have a 5-carbon linker, lipophilicity goes downwards. Okay. So the perturbations experienced by the oxygen will be, the perturbations in whatever the CF3 is doing are going to be felt when the CF3 group is close to the alcohol, but not as it gets too far. Cool? Makes sense? Okay. So this change in lipophilicity, the use of fluorine to make things more water soluble can be really useful for various reasons. We'll see some issues with metabolism addressed by this type of property tomorrow, but it can also decrease lipophilicity when used intelligently and systematically. So this is a nice slide from David O'Hagan's. Well, the slide is great. It's my slide. It looks great, right? No, it's a nice study by Dave O'Hagan in which they're looking at lipophilicity of a series of compounds, and this is by phenyl and cyclohexane, phenyl cyclohexane here, pretty greasy molecules. You can tune the lipophilicity, make more water-soluble compounds by patterning the fluorine. So you can see the syn arrangement here, the 1,2 arrangement. Look at the magnitude difference in that matched pair right there. Remember, those are log units, right? 1.5 log units is a lot there. We can put another fluorine atom in, further drive it downwards. You can see that the stereochemistry of the fluorine has a little bit of an effect there. So that's interesting. If you have this one, what would this be? A 2, 3, 4, 5 phenyl cyclohexane, all syn. Look at how much we've driven water solubility, right? 2.5 p units, that's a lot. And what's going on in this case is that we are actually improving the interactions with water, right? In order for something to be water soluble, you need a hydrogen bond with water, either as a donor or an acceptor. And in this case, the fluorine atoms, being sigma withdrawing effects, make the axial hydrogen atoms on the bottom face acidic. And when they're acidic, they can hydrogen bond with water. The lone pair of electrons on water being the acceptor, the acidic protons being the donor. Okay, you can use it strategically. This is a fluorine-induced perturbation, and it's due to the strong sigma withdrawing effect of the fluorine atom. Okay, the electronegativity effect. Make sense? Really cool example here of fluorine when patterned properly on an aliphatic scaffold can drive water solubility so much. Really nice example. And this can be combined with other substitutions that also improve water solubility. So it works if you have other hydrogen bond donors or acceptors in the molecule. Here's a series of anilines. We don't always want anilines in drugs. You have other oxidative issues when you have anilines in a drug. Carboxylates, you find those on some drugs. But the trend that fluorine patterning can drive water solubility also works in these other settings. Okay? So we're going to see how these types of substitutions affect metabolism in the next lecture. And as medicinal chemists, you always want to be aware that when you're trying to change one property, there might be other changes also going on in your molecule. So you have to be able to track all these different parameters. So even though we're trying to influence lipophilicity, what's it doing to metabolism? What's it doing to any of the other metrics that I'm using to track my molecule? So you want to have this like multifunctional processing unit in your head to be able to track everything there. So that was aliphatic systems. Okay, in aliphatic systems, if you fluorinate, it's strictly aliphatic. You start fluorinating and you fluorinate intelligently, you can drive water solubility. So in the next series of examples, we're going to talk about aromatic systems that are extremely common in drug discovery. Plenty of arrow rings and hetero-arrow rings in drug discovery. Well, if we start introducing fluorine onto those, what happens to lipophilicity? And that's what we're going to look here. And when we look at these, we use a pi parameter. Pi is a parameter used for linear free energy relationships, which you've seen in physical organic chemistry. And it's basically looking at the logarithmic, at the log of the difference in log p, between benzene and whatever your substituent is. Okay, so we're looking at a delta log p when we say pi parameter. And so we'll just look at a series of these with benzene being the 0 point for this analysis. A single fluorine atom increases lipophilicity barely. 0.1 units, 0.15 unit, not too much there, but there's a little bit of an increase. Just for comparison, if you put a chloro substituent on there, 0.7, that's a greater magnitude. And if you think about a methyl group, that's a half log unit. So if you put a fluorine atom on there, there's a minimal change, but not too much. And that change goes the opposite way of what we saw in the aliphatic system. In the aliphatic system, we lower log P with a single fluorine atom. In an aryl system, we increase log P. Okay, so what it's attached to matters. Now, we can go ahead and take the methyl versus CF3 example and compare those and recognize that you get a further increase in log P when you fluorinate benzoic position. So the benzoic position going from 0.56 to 0.88 is definitely an improvement. But when you think about the magnitude of the change per fluorine atom, it's not very much. Delta log P between these two here, you can do in your head really quickly, right, about 0.3. And that's not much when you have 3 fluorine atoms. Each fluorine atom is like 0.1. So you're not getting a huge change here on these simple model systems as you fluorinate directly on the ring or on the benzoic position. Little change, but not all that much. Now, if you start fluorinating further away on the regular aliphatic system here, then you see a bigger change. And again, that's an ethyl group. So we go back to the paradigm that we saw right at the beginning, that we're just fluorinating on like a regular aliphatic system as you get away from the ring. Okay? So you can keep those in mind. As we continue to walk through, what we'll realize is that when you fluorinate, adjacent to heteroatoms, you get huge perturbations. And we started to see that on the first slide. Okay, as we had our ethanol, propanol, butanol series, and we saw the magnitude of the effect was great on ethanol and less and less and less as you move the CF3 further and further from the oxygen. Now we have the CF3 attached directly to the oxygen, and the delta log P there is about 1 unit. And I'm looking at these two over here, the anisole versus the trifluoroanisole there, 1 log unit, big change. So how would you explain that? What drives water solubility? Hydrogen bonding with water. So what is CF3 doing? Let's just start with anisole. With anisole, what's engaging water? Dipole, and we also have lone pair of electrons.
So the kind of hydrogen bonding, I mean, that is hydrogen bond acceptor, and water is donating the hydrogen.
So you have a donor-acceptor interaction, like the OH, the H is the acid in this interaction, and the oxygen is the base in this interaction, the lone pair of an oxygen. And if you fluorinate, what happens to the basicity of the lone pairs on oxygen? decrease, right? The sigma withdrawing effect between the CF3 and oxygen starts pulling electron densities toward the CF3. Oxygen, as a result, kind of retracts its electrons a bit. They become less basic, less engaging with the water. 1 log unit difference in that matched pair. Right? Makes sense when you think about it? Okay. So we can keep going on. The same is true if you have other heteroatoms here. If you trifluoromethylate thioanisole here, you can see a significant difference there. Not quite as much, 0.8 units, but that's still pretty significant. You can see you have sulfones, you get a big change there. Again, the perturbation is through a couple of atoms, but in the SO2 group, it's the oxygen atoms that are basic and engaging water through hydrogen bond donating, accepting interactions. And that CF3 group, again, forces the retraction of those lone pair electrons that are less basic, less nucleophilic. So there are more and more examples. I think we've walked through in detail enough, but you have more examples on your slides, and you can look up these parameters also in various texts and references. There are some lists you can find online if you want a comprehensive version of these TAF parameters, but I've just selected, the pi parameters, but I've just selected a subset of match pairs from fluorinated versions, okay? So there are other common substitutions that we encounter in medicinal chemistry. This table looks like a lot, and we're not going to cover in detail every single example. I'm going to summarize some general trends. It's common to take a hydroxyl group and replace that with a fluorine. Now, sterically, this is a pretty reasonable change. When we started on day 1, many of the steric parameters for a monofluoro group were similar to the oxygen. Like this was like the very first slide, lots of data on it, looking at bond lengths and the size of the atom. So this is an isosteric replacement. It's pretty distinct because you have a hydrogen bond donor here and nothing there. Okay, so you're definitely going to get different properties. I'll explain a couple of general trends. If you have electron withdrawing groups on your ring, there's a reasonably modest effect across the board. You don't seem to perturb lipophilicity greatly. But if you have electron donating groups, you do see a significant perturbation. Okay, so it's a general trend. There are a lot of details and nuances within the data. But I think it's a good exercise for individuals to think critically about why. Okay, so I'm gonna leave that for something to go home and think about. Maybe after you think about it a bit, we can come back like in the next class, like right at the beginning, the first 2 or 3 minutes, and look back at this and see what you all think about that. Okay?
I'm particularly interested in that what is not highlighted, that F. When you have a difluorinated, difluorine functionalized aromatic ring, so you see that in the para position, so you have the delta log P, that is 0.36, but in the ortho position, you see there's I think that's significantly big, right? 0.6.
Greasier? Yeah.
So basically ortho position, if you have a fluorine OH or a fluorine, then the log P, if you change it to fluorine, the log P changes more. That means it becomes more lipophilic as compared to what it would be in the OHF. So what is the reason? Because that's OH was, of course, OH was doing hydrogen bonding with water. But in this particular case, this change is much bigger in the case of ortho.
Yeah, I think it's a really good question, and I haven't thought about that pairing yet as I was going through and preparing this. I'll have to think about that more. You know, it's the delta, right? The difference in this series here, but it's not just which one is the most. This is a change in lipophilicity, which is a bit trickier to think about. Yep. I don't have a great answer for that right now, just off the top of my head. So it's a good one. Another substitution might be a methoxy group for a fluorine atom. In this case, you have hydrogen bond accepting capability here. And maybe, that's pretty weak here, not very good. But you don't have the hydrogen bond donor. And when you have this type of situation, things are all over the place. You do not have consistent trends. But most of these perturbations are reasonably minor. Okay, so this substitution is reasonably isolipophilic within a little bit of error. The magnitude of the changes rarely get up to half unit. Most of them are less than 0.2 or so. Okay, so these are pretty minor changes, and you can get away with them without causing too much of an issue with changes in log p. Okay, so that's the main story here. These are reasonably close to each other in terms of lipophilicity. Okay. You can make these changes on heterocycles. The manuscript I have here has a wide variety of additional examples that you can dig through of increasing and increasing complexity. So if you want to see real-life examples of therapeutics and candidates, you can see that. When you fluorinate in the vicinity of heteroatoms, you get the bigger bang for your buck. Okay, so that's where you get this massive change there. As you get away from the heterocycle, that change drastically it falls away. So you can see the magnitude of the changes again on the heterocycles. If the fluorine atom is further away from the basic moieties, you see a minimal change. Okay. Questions on these ones?
So if you compare the trimethopsiphenol that we have already seen, that
Trifluoroanisole.
yes.
Yep.
So in that case, the lipophilicity was decreasing, right? But in case of that pyridine,
Coming over here?
yes.
This example here? You said is that what you're talking about?
Earlier one.
Earlier?
At the dipole. No, here itself. So lipophilicity is increasing, right?
Yep.
But in case of that pyridine, what is happening? That I want to.
Yeah, so the pyridine has a really strong hydrogen bond donating and accepting potential because you have an acidic proton, the O has basic lone pair of electrons, and nitrogen has basic lone pair of electrons. When you make this substitution, you lose the hydrogen bond donor and acceptor, and you also minimize the hydrogen bond accepting ability of the pyridine through an inductive effect. So you have multiple things that are changing all at once with one substitution. So there's a lot going on in this example. Yep.
So in the previous slide, like when we are replacing in those tables, like CF3 is like decreasing the lipophilicity as compared to CHO and CN, although like CF3 also has protein.
No, so these are not, are you trying to compare these values?
I mean, like fluorine versus CF3.
Right. This one versus this one? So you can't actually compare these values because this is delta log P for a matched pair. So it's the difference between the phenol bearing this versus the fluoro bearing this. And so you can't do a full match, like you can't compare this number to that number, I don't think, directly.
The orthoposition of the fluoro group that can be explained through hydrogen bonding. If that fluoro is engaged with hydrogen bonding with OH, that time it will be that lipophilicity will be high. But if in case of CF3, that hydrogen bond we cannot, maybe not possible, which decreases its intra-hydrogen bonding, not inter. So that increases its lipophilicity, decreases lipophilicity.
Yeah, so delta log P would be greater here because it's intramolecular hydrogen bonding interaction that's being disrupted or introduced depending on which way you're going. And yeah, I'd have to think about it. There are some, that's a complex topic. Who did that? There's a series of studies looking at phenols and benzyl alcohols and the intramolecular hydrogen bonding differences with like exactly these types of questions. I can go look up the name in the break, and there's a series of papers looking at those types of things. Yep.
Yeah, like because orthopyridine example, orthofluoropyridine and orthohydroxypyridine. So something very similar is happening in this example also, because now we are comparing orthofluorophenol versus the orthodifluoro. So with the difluoro is now removing the possible hydrogen bond donor acceptor capacity, the OH is gone, and plus it is also affecting the hydrogen bond capacity. So I think that also little bit explains, similar to like chlorpyridine case, that increase, that 0.66 might be.
Okay. So we can also look at other substructures. Other common perturbations in drug structures might involve the replacement of a hydroxyl group with CF2H. As we'll learn in Friday's lecture, CF2H can serve as a hydrogen bond donor. So the two CF3 groups, sorry, the CF2 group, the fluorine atoms, through an inductive effect, acidify the geminal H, and that can then serve as a hydrogen bond donor. Okay, so this substitution of an OH versus CF2H is used sometimes. There are different estimates about how strong of a hydrogen bond donor it is, so it varies based on what type of a metric you use, but there's the capability of doing that. The second substitution that we'll look at is going to be a methyl group versus a CF2. And we'll start to walk through some of that data really briefly. In the first case, as we look through this series, the OH to the CF2, that's on an arrow ring here. So the OH versus CF2 increases log P, and that makes a lot of sense because the CF2 doesn't have basic lone pair of electrons. Okay, it can't hydrogen bond with water very well through as a base. And in contrast, the phenol can, right? The phenol has an acidic proton and it has lone pair of electrons on oxygen, so the water solubility is going to be better there. And you see that in this series. In the second series here, we're replacing a methyl group with a CF2, and we do increase water solubility. In some cases greater than other cases, but overall you see changes there. When we come into the second series here, we're going to look at ethers and sulfones and do the same comparison. So if we have it, in this case, the group directly attached to an oxygen, we're not looking at peroxides. We don't use those in drugs, right? So we can't do these ones here, but we can go ahead and look down here and say, what if we have a methyl ether in an aliphatic system relative to a difluoromethyl ether on that system? And you see a big 1 log unit change there and a 1 log unit change when you look at a methyl sulfone compared to a difluoromethyl sulfone. Okay, so you can again get reasonable perturbations and lipophilicity. In this case, we still use the same explanations that we're perturbing the nucleophilicity or basicity of that lone pair of electrons on the heteroatoms that are in the direct vicinity. And that's the reason why we improve lipophilicity in these cases. Cool? Okay. So you have to look around the molecule, and when you're putting fluorine in, are you closer to heteroatoms? Are you making perturbations there? Are you an aliphatic system? And then you'll get a better feel for which way you're likely going to drive lipophilicity. So in the next series of compounds, we're going to talk about the acidity and basicity of acids and ethers. Yep. Yeah, so is this for tea?
Yeah, I just want
Okay. Give me a second here. Where's my cursor? Yeah, we'll go 25 minutes. 25 minutes. Okay, there we are here. So let's come back here and we're going to talk about carboxylic acids. We know about carboxylic acids in general. There's a common reagent we use, TFA, deep protection of Bach groups, and other transformations sometimes too. We say that's a pretty strong acid. It's a sigma withdrawing effect as you take, in our model system here, just acetic acid and start adding halogens you perturb the acidity and increase the acidity, and that increase correlates with the electronegativity, right? So that more electronegative elements, as we add iodine, bromine, and then fluorine, increase the acidity. And again, that's just the inductive effect that we use to rationalize, and that's additive. So as you add in one fluoro group, two fluoro group, three fluoro groups, you see this sequential increase in acidity, and it can be pretty powerful because relative to acetic acid, we've changed over 4 log units, over 10,000-fold more acidic. And we can see that when we look at some other heteroatom base groups also. And then you can also pattern fluorine around aromatic rings and perturb the acidity and basicity of the atoms that are attached to the ring. So this is a benzoic acid that we're looking at, and a perfluorobenzoic acid, and you can see a pretty substantial change in the lipophilicity, sorry, in the pKa of those species. The same is true with alcohols. Now we're going to start rationalizing the data that we saw on the initial slide and really connect the log P from the first slide we covered, the changes in log P, we're going to connect them to the acidity and the basicity. And it really is the basicity that tracks most critically here. The basicity of your oxygen and nitrogen heteroatoms that really drive the water solubility and the lipophilicity changes more than the acidity term. Okay. So let's look at this series of alcohols. We already saw ethanol and trifluoroethanol there. You can see the pKa change. Look at that change. Over 3.5 log units there. The acidity, that's alpha. You can see the definition of it right there. So the acidity, the donating ability, our acidity is there. The donating ability is here. The donating ability is a hydrogen bond donor, allowing that hydrogen atom to increase. The CF3, being more acidic, allows that hydrogen bond to make better interactions with water, perhaps. It's more acidic. It's a better donor. But the basicity of the lone pair of electrons on oxygen are stronger for ethanol relative to trifluoroethanol. Okay, and this is a really critical data point here. These are measured values. The basicity is higher. The basicity of the oxygen is what makes the hydrogen bonding interaction with the H of the OH, right, of water. Okay. So the main perturbation here is really the change in the basicity of the lone pair of electrons that drives the changes in log P, more than the acidity term does. Okay. And the same is true as you look at further and further down this chain. There's a series of alcohols here, so we can look at isopropanol and HFIP here. Big change in log P, perturbation in the hydrogen bond donating capability, and the accepting capability. Again, the accepting capability is what really drives the change in lipophilicity here. It's a loss of water solubility that really drives it. Yep.
So, okay, the alpha is the hydrogen bonding donating ability, beta is the accepting ability. So, hydrogen bonding accepting, this is a base, right? So, we see in these two cases, the one you are currently highlighting and the other one, that the basicity is increasing because H bonding accepting ability is increasing, right?
I wouldn't say it's because. I mean,
Okay.
they're happening,
Yeah,
but yeah.
that's okay.
Yeah.
But then the other side, when I look at that alpha values are decreasing, right? So it's not a good H bond donating ability, which means it's not a great acid.
So it's less acidic.
Less acidic, right?
Right. So that means that the acidity is not what's really driving
Okay. No.
the changes.
Because I was correlating with the pK value. No, it's fine.
Yeah.
It's fine.
Yeah.
pK value is decreasing because even though it is not that acidic, the pK value is pretty high. It's actually in basic range of the conjugate, the bases.
Mm-hmm.
So so that's okay. It's dropping marginally. Yeah,
Mm-hmm.
that's okay.
Okay, so the same can.
But I think that had you put it in pKb value, then beta 2 we could have probably correlated well enough. But that's okay.
Yeah.
This is understood
Yeah.
from there.
Okay. So again, there's more examples and to dig through. That the trends are generally the same. Yeah, we had another question.
One more question is that regarding carboxylate, right? So if we compare the pK value of methylene iodide, methylene bromide, methylene chloride, and methylene fluoride, right? Here, right? So lesser will be the pK value, right? So in case of if you compare the CH2I and CH2F, so the pK value of CH2I is quite means higher as compared to CH2F.
BR? Yep.
But iodide
But
is
it
not
tracks with electronegativity.
iodide is not a means too much electronegative than fluoride. Fluorine is
No, fluorine's way more electronegative than iodine.
fluorine is more
Yeah, yeah.
electronegative, right? So
So what we have is increasing electronegativity
right.
and then increasing acidity. Yep. Yep.
I got confused.
Okay. It's all good. Okay. So, there are a couple more examples. The trends are generally the same. The key here is that it's the basicity driving the water solubility, and that's where you get, when you perturb the basicity of the heteroatoms, that's where you see the big changes in lipophilicity. So, yeah.
Yeah. So I just had one question because I was thinking about planning some of the work what we are doing in the lab based on this data. Very interesting data. So these are all the values are the real values, pK and log P values, are the computational values. Or how much they correlate?
I don't recall if these are computational or experimental from when I pulled this. I probably made this part of the slide deck in 2017, 2016, and I don't remember exactly.
My point was asking was that how much they correlate, like if there is a real values and computational values, so that maybe we can prepare a set of like all possibilities what we are expecting, and then plan the synthesis.
Yeah, I think that's something to, as you're applying it in your own, I mean, we can look back at the resource and find a couple of the original references too and figure that out. Yep.
Yeah, because in our drug discovery process, like some molecules, we want to improve the pK or at least the solubility because the target receptor is inside and it has to pass the outer membrane. So maybe improving the solubility might help. Right now we are not in set up with PK studies, but at least I was thinking that we can use the computational values and then plan which modifications we should do.
Sure. Yeah, we can discuss details. So these trends are also, they also correlate with drug-like structures and cyclic systems too. We'll come and start talking about cyclic systems a little bit more later when we talk about amines. Nonetheless, you can see changes in pKa and eventually log P as you fluorinate, and as you rotate the fluorine atom to different positions, you actually see different perturbations. Okay, so the closer you get the fluorine to, in this case, the carboxylic acid, the more powerful the effect is relative to when you rotate the fluorine atoms further and further away. Okay, and that's true in both cases. We have a case where we have a carbocyclic scaffold and an ether scaffold. And as you go from the carbon-based system, again in this data, to the difluoro, you see you see changes in the pKa of your groups. Okay. Cool. Good.
What was that one in the bracket and what is the difference? 2.81 versus 2.5.
Log P.
Okay, sorry, I missed it.
Yep. Sorry, I think I mentioned it, but didn't point at it. So pK and log P are both on that. Yep. Okay. So let's talk about just a couple of other functional groups. You don't necessarily see ketones very commonly in drugs, but we'll talk a little bit about some specialized ketones in the very last section, like one of the last couple of sets of slides. And so the perturbations are still relevant. The perturbations in basicity are relevant for carbonyls. So if we have acetone and trifluoroacetone, you can see a pretty profound effect in the basicity of those lone pair electrons, as shown here. In addition, you have the perturbation of the acidity and basicity of amines. And the perturbation on amines is like one of the most impactful things in drug discovery. So if you can perturb the basicity of amines, you can change all types of properties. And you'll see some more of that in the second half of the lecture. So if we have an aliphatic system, just ethylamine versus trifluoroethylamine, you get a huge change in pKa. And that change is super, super, super important because you can take an amine that's typically cationic under physiological conditions and make it neutral. Okay, so physiological pH about 7.4 in normal tissues or in plasma. We can take a basic amine here, typically protonated, pKa of nearly 11. That's going to be near fully protonated. And look at that pKa, it drops down several log units. It's below 7.4, it's below 6. Now we're neutral. And you see a change in the basicity of the lone pair of electrons on the amine also. Look at that change. Much less likely to engage with water as a hydrogen bond acceptor. Okay? It's going to change log P pretty drastically. And the same thing can happen on anilino systems. We can perturb the pKa of the aniline pretty drastically if we pattern fluorine properly around the ring. In this case, we're looking at perfluoroanilines. There's 5 fluorine atoms, but you would still see an effect of lesser magnitude if you only had a couple of those fluorine atoms. Okay? So really important things to look at and think about. These changes, again, can be seen in carbocyclic systems. The perturbations here going from non-fluorinated. You can see the data, the pK and the log P. These are pretty profound changes when you're dealing with amines. So we have the carbocyclic systems in red, the ether system is in blue, and you see as you introduce the gem difluoro group a couple of atoms away, alpha, beta, gamma, so that's the gamma position. You can see a significant drop in the pKa and the lipophilicity. That one should actually go up a little bit, so that's 1.69. If we rotate it even closer in here, you see a further perturbation in the pKa and the acidity of those. Okay, really important, really valuable for drug discovery. In both cases, this would be half protonated at physiological pH. This would be not protonated at physiological pH. Okay. So there are algorithms for predicting, just on the back of an envelope calculation, you can predict the perturbation of pKa with a really simple system here. You don't need sophisticated computational methods to do a quick estimate. Okay, maybe you need to do those for your project, but you can also do a quicker estimate this way. What you do in the system is you identify the distance between the amine and the fluorine atom, however many fluorine atoms you have in your molecule, identify the distance. And we talk about distance for this chart. We're talking about distance in Greek letters, so alpha position, beta position, gamma position, delta position, right? So that's the way we count in the system. And then the perturbation based on the distance is shown here, the delta pKa. Okay, so you have one fluorine atom, beta, think about minus 1.7 units, gamma, minus 0.7, delta, epsilon, you can see those values. The magnitude of the change decreases as the distance increases. So here's a couple of examples of how you would use it. You take the known pKa or calculated pKa of your amine. For a cyclic system, we actually have 2 paths that we need to follow. This is a single fluorine atom, alpha, beta, gamma, it's at the gamma position, but it has 2 different paths, so we have to actually count both of the paths. So the perturbation in this case is path 1.7, but also path 2.7. So you would anticipate a change of minus 1.4, and this is, for a quick calculation, 1.7 is pretty close, minus 1.7. If we rotate it over, now our chain length changes, right? And so we have alpha beta. The beta is minus 1.7. When we go the other way, that's going to be a delta, and so we have a change of 0.2, and it's minus 0.8, or 1.8, okay? If we have 2 fluorine atoms, 0.7, 0.7, 0.7, 0.7, we get a change of 2.8 pK units, negative change, and experimentally 2.6. So there's a little bit of error with these calculations, but it's an initial estimate that you can use. Okay? We good with using this for quick estimates? Okay, So let's start putting more and more and more together and think about how this applies in real life systems. I keep coming back to this figure here. In order for a drug to cross a membrane, it needs to go from a hydrated state to a dehydrated state. Now, this dehydration does not necessarily occur in solution, in plasma. Okay? Many times this dehydration occurs as the molecule is passing through the membrane, so the greasy part starts going into the membrane, and then the water falls off as the molecule continues to go in. So recognize it's tough to draw that process on a little 2D slide like this, and then it'll rehydrate eventually once it gets through the other side and it comes out the other side of the membrane. And log P, as we look at the data, is the ratio of octanol solubility relative to water solubility in that shake flash method, and that mimics whether the molecule is going to be happy enough in the greasy environment in the membrane, and if it's water soluble enough to come out the other side properly. Okay. Now, fluorine perturbs the acidity and the basicity of the heteroatoms attached to the drug. So it'll make a more acidic hydrogen bond donor a less basic hydrogen bond acceptor, and we typically correlate the changes in lipophilicity with this property over here. We walked through that, but I just want to come back to the main big picture here. The main effect of fluorination on lipophilicity comes to perturbing the basicity and then the engagement of water here. I said it a couple of times, but I wanted this picture to be bold and in your face so you can think about this as you think about molecular design and drug discovery. So let's look at a couple of examples now that we've looked at a lot of data and a lot of model systems. Now we can actually start looking at drug structures. This is the one that we saw yesterday. And so this is an example of a serotonergic agent. The binding data here is typically in nanomolar for this series. The initial lead compound is basic. This nitrogen is basic, pKa of nearly 10. It's a reasonably potent compound, but poor oral bioavailability. Okay. Mainly because that amine is cationic under physiological conditions. If you have a plus charge on your molecule, is that going to get into a greasy membrane and be that happy? That plus charge is going to be reasonably hydrated. So in order for this molecule to pass into a membrane, it needs to get into a neutral state. And for it to be neutral, we can adjust the pKa, the basicity of the amine, using fluorine. You can see this example right here. A single fluorine atom can perturb the pKa about 1 unit there. We lose a little bit of potency, but the bioavailability shoots up. You can get through membranes better. Remember, protonation states, they're ratios, right? These are logarithmic ratios of being protonated versus non-protonated. So if you have enough of the compound neutral under physiological conditions in a reversible equilibrium, then it can still get through. The neutral part can get through, the cationic part might not. But it's an equilibrium. That proton's going on, off, on, off, on, off. So we get a good bioavailability here. For engagement of the receptor, and for many CNS drugs this is true, for engaging the receptor, many times you need a cationic amine. You need that amine to be protonated. So you need a little bit of basicity in the molecule. So if you put a second fluorine atom on the molecule, you lose potency pretty significantly. So you can push it too far the wrong way if you put too much fluorine on it. Okay, but look at the change in pKa. We have 3 log units relative to the parent compound there. Okay, so if you needed that thing to be always or as much as possible neutral, that still might be a good substitution. You just can't do that with a lot of CNS therapeutics. And you can perturb that basicity even more with other heteroatoms. So the sigma withdrawing effect, oxygen is pretty electronegative too. So you can see that type of a perturbation of pKa just for teaching purposes. You can regain some potency because the receptor still accepts a hydrogen bond accepting group at this position. So we regain some potency, but still not as good, still not in the 300 picomolar range, but I think it's a good instructive lesson for how powerful modulation of pKa of amines can be using fluorine. So this is the last example before our break. So this is an FDA-approved therapeutic. Yep.
Yeah, sorry, I had one.
On this one? Yep.
This was again very interesting example. I was just trying to correlate the activity change with not only the electronegativity but also the conformational things what we were discussing in the last class. Like because of the fluorine, is it also possible that it is changing the conformation such that maybe the activity also can be lost because of the that specific conformation which is difficult to fit into the problem?
Yeah, sure. There could be conformational consequences of fluorination that they're not discussing. This is a 99 paper, so maybe a modern analysis or reanalysis would have a different an additional interpretation. Certainly think about the conformations would be relevant. Perhaps it'd be really interesting to make the two enantiomers fluoro, R versus S, and get a feel for maybe one of them super, super, super potent, and the other one is like not as good. Maybe there'd be something good. I don't know about the value of 5-HT1D right now, and if people are really excited about 5-HT1D. So there's also a should you do it. These serotonergic agents could be kind of tricky, and a lot of other things can happen when you're messing with serotonergic receptors. I don't know the recent history of 1D and how good of a target it is. So this is Januvia. This is an FDA-approved therapeutic. This is a fluorinated drug. The accepted drug is right here. It has the CF3 group. And this is a study in which we will look at a series of compounds in which we change the substituent R1 right there. Okay? So in terms of inhibitory potency, you can see the series of values here. For the series, the hydrogen is a little bit less potent. You get a slight improvement in potency as you put in the ethyl group, a little bit of grease there, a little bit more potent with the CF3. If you get too big in that space, you lose a little bit of the potency, but 71 nanomolar is still pretty good, right? So not big change there. As you fluorinate this molecule, there's a little bit of change in the clearance, the metabolism, but it's not substantial. It's not a big driver here. These clearance rates and the half-life are reasonably close to each other. The big changes you get here are in the distribution. So Cmax, that's the maximum concentration of the drug through an oral dose. In this case, if you dose this drug orally with the AH or the ethyl, none of that gets in the body. That thing does not get into systemic circulation. And when you put fluorinated groups at the position right here, the 2 position of the heterocycle, now we start to see substantial concentrations of the drug in the body. Oral bioavailability, this is F, this is the percentage of the drug that enters into systemic circulation with an oral dose. That goes from single digit up to 70% with that fluorinated substitution. And the rationalization here is that we're perturbing the basicity of these such that they dehydrate well as the molecule is approaching the membranes. Okay, so that's the rationalization there in terms of pKa's. This is one that I'd like to do and send somebody off to go say, you go do the calculation and convince yourself that there's a change in the basicity of these positions. And you would want to be protonating this and making the amine, protonating this and making the heterocyclic protonated form. And I think this is a good exercise, again, for somebody to go do and calculate the pKa's of those and convince yourself that there's an important change there to track. So we do have a couple of other examples in the afternoon that are going to have a similar heterocycle where we do have some data to look at there. So I'm covering that scientifically. I'm comfortable because of what we're going to see later. Okay. So are we close enough to on time? We can pause for a little bit now. It's a good time for a tea break for everybody, and then I can reset myself mentally for the second half. And we'll have a good, thoughtful discussion in just a little bit, all right? Cool.
Yeah, I just wanted to make a note here. So I think Mr. Atman has given the wonderful examples. So just if you just think about now any other example, like suppose instead of fluorine, in your molecules, if you have fluorine, methoxy, or cyano, any other groups, then the concept will remain same because the inductive effect, the conformational effects, and its change on the pKa, pKb, or the other IC50 values whatever you see. So definitely I think this will be definitely useful even though if you are not into fluorine chemistry also. These concepts as a medicinal chemist, they are really amazing. So those who actually will work eventually in the pharmaceutical R&D labs, you will see that now R&D works they not only try to improve the activity of the molecules, IC50 or EC50, but they also want to improve the PK properties of the molecule. So that's why I think these discussions will become very, very useful. Okay, so I think with this note, let's break for a tea.
What time do we come back?
Yeah, 15